platforms. Go for it.
All right. Thanks for having me, everybody. And as I sort of warned you during the discussion section, most of what I was rambling about earlier is basically the talk, so we can go maybe a little bit faster. Also, I'm going to thank Natalie for doing an amazing introductory hour-long discussion of high energy physics so that I can also skip some of that. But fundamentally, high energy physics requires quantum computers if we want to solve theoretically interesting problems. There are a bunch of things across the entire gamut of high energy physics that firmly sit within what we consider to be BQP. And these things include, as we were discussing, the obvious things of collider phenomenology and doing scattering. If I want to solve strongly interacting matter like the neutron star, if I want to do early universe cosmology, if I were to be really ambitious, non-perturbative quantum gravity, all of these things we expect to require quantum computers to efficiently solve them in any practical amount of time.
You can't see the slide deck.
You're not seeing the slide deck, Eric. Well, you've seen the slides, Eric, so.
Well, I was trying to be nice for everyone else.
That's fair.
Or can we see video? Okay.
Happy?
Yep.
Cool.
Thank you.
So me personally, I come from a background in lattice gauge theories and lattice field theory. So just to give you a quick summary of what lattice gauge theories on a quantum computer might look like. So in order to render quantum field theory usable on either a classical or a quantum computer, you have to truncate in the finite volume, you have to put it onto a lattice, and you need to truncate the fields in some way because these fields, the bosonic ones, are normally going to be an infinite dimensional Hilbert space, and therefore you can't put them on a finite computer. So you have to make all of those truncations. And if you start imagining all of that being done, the consequences for what the architecture needs to look like is that high local connectivity is almost a must for us. We're talking about doing 2- and 3-dimensional lattices of field theories. So we want to simulate those types of theories. And each one of the lattice sites and each one of the links of the lattice is going to have something like an n-qubit register independently for it. So each of these n-qubit registers then needs to be connected to all of its nearest neighbors at least in order to do the calculations we want. So if you start thinking about sort of the primitives that I might put onto these hardware devices, we're talking about having 2 times n all-to-all connectivity in order to be able to simulate these things in the most efficient way possible. And as you move away from that, you're gonna have to introduce swapping, you're gonna have to introduce new hardware techniques and things like that. And as I sort of also said, we would really prefer if we can do periodic boundary conditions either virtually by swapping around qubits or by actually having the topology of the machine be designed in that way. And all of this sort of leads you to say that qudits sound like a really clever idea, and that's part of why SQMS is excited about designing qudit-based platforms. As sort of Natalie was discussing, and as we've talked about several times now, the interesting field theories for doing real high energy physics are the ones that exist in the standard model, which include QED, electroweak, and QCD. And if you're willing to accept my very hand-wavy arguments, those are sort of the per link cost in terms of qubits that I'm estimating are necessary for us to do each of those links. And those numbers are highly negotiable and highly controversial, and depending on what representations and visualizations you choose, they can be different. But this is sort of the ballpark of what we think is reasonable to do interesting physics with. Oh, it's not progressing because it's no longer on that. Sorry about that, everyone.
So can I ask a question? I mean, how did you come with this? Yeah, I know it's short time, but with these values of n, I mean, the presumption here is that for these values, you already can see some universality properties. And
yeah, those numbers are my numbers, which are saying I'm going to take the best case scenario discrete subgroup approximation of those various continuous groups. And that's where those numbers, so I can compute those numbers trivially for you, whereas other truncations can't. But there are an infinite number of problems with my choice that doesn't bring this one. So again, what I told you already, today's estimate is that we need 10 to the 8 logical qubits and something like 10 to the 59 T-gates in order to do a particular problem. What is that problem? That problem is, as quoted from the exact paper by Can and Nam, as I said, is our analysis shows that 99.998% of the gate count stems from doing quantum fixed point operations. And this suggests that the SU3 heavy ion collision problem is only going to require a little bit less than 3 years of runtime on an exascale quantum supercomputer. So this is the closest we have, as of right now, I would say in high energy physics, to an estimate of what we realistically think we would need. So where do they come up with this number from? So the first thing they say is we're going to take the Kurkcuoglu Hamiltonian, which is sort of the standard Hamiltonian for gauge theories that we usually talk about today, and they're going to put it on 100 cube lattice. They then say, well, we're going to use a different truncation than what I would normally use. They use an electric field basis truncation that uses this lambda as a cutoff scale, and they estimate that using 10 for that cutoff scale, it's going to take 24 qubits per link. They then say that we're going to use trotterization, and then we're going to use the sort of standard, computer science-based techniques for estimating what the error is going to be from a trotterization simulation. And then we're going to decompose the specific Hamiltonian with a specific set of hardware assumptions into a specific set of unitaries that introduces some synthesis error because we can't exactly reproduce the continuous degrees of freedom and things like that. And then finally, they're going to impose the constraint that their total error is going to be 10 to the minus 8 in the sort of standard computer science language. So those are the assumptions that lead you to those estimates. So, what would it really take to do a practical quantum calculation? So the rest of the talk, as long as I have time, is going to be about how we can understand that those numbers, while scary, are not probably what the real state of the field is. So the first thing to point out is that any lattice QCD calculation, you can sort of do the naive guesses of how many qubits and how many gates you're going to need just by saying, what is the physical volume I need to simulate, and how finely do I need to divide it? And then, clearly that gives you the number of qubits. And then the number of gates is just going to be some function of however many lattice sites you have to put down times the total time you have to run this thing divided by how finely you need to resolve it in time. So those are sort of, the back of the envelope calculations that we were talking about that like Peter Love and I have written papers about where you do this kind of analysis, say this is roughly where we're going to land. Now, if you think about doing Jordan-Liam-Preskel particle scattering of a proton and a proton, then what you need to do is you need to have two protons that are isolated enough from each other, have them come in, collide with each other, and then go back out. Or, if you're going to produce particles, you need to allow enough time and enough space that you can resolve all the independent little particles. And so if you want to be really, really aggressive and put it into a reasonably tight box, you can imagine taking these one Fermi protons and putting them in something like an order 10 Fermi box. So that gives you a little bit of separation between them. And then you imagine that if you want to do physics with protons colliding, you need to have something that's sub-proton radius resolution. So you need something on the order of like 1/10 of a Fermi box. And so those two numbers together right there for both the time and the resolution are where you're getting these 100 lattice sites per direction are required. So that's terrible. So if you go through this exercise and think about things like the Parton distribution function, or you think about transport coefficients, then you realize that the physical scales that come into these problems can be different than what hadron scattering is. And therefore you can get a gain just trivially by saying that was a very difficult problem. Let's not do the most difficult problem. So a much simpler problem is to compute things like the viscosities of the quark-gluon plasma. We're doing like thermodynamic, non-equilibrium type physics. And then, instead of having this, 2 order of magnitude hierarchy, you have something that's sitting both in resolution and in volume of the same order of magnitude. And so you sort of trivially have saved yourself, an order of magnitude in qubits at least. So choosing better problems and establishing what they are in high energy physics is not a settled point, whereas sort of, in generic quantum computing, quantum chemistry, and other field domains, there's sort of an agreed upon sort of metric problem that everyone's working on.
Are you saying that you're in the second bullet point, those are coarser, effective variables that you wish to compute?
Yeah.
Okay.
Yeah, that's the intuition, yes. So what exactly is the algorithm? So, if you're doing Jordan-Liam-Preskel, you need to do adiabatic state prep of 2 particles that you don't know how to prepare, have them collide and have them come back out with a very long time. If you want to do something like viscosity, again, this isn't a fully worked out algorithm in the sense that we can give you total gate cost and things, but the picture you should have is I need to do thermal state prep, followed by a pretty hard quench, and then just allow some trotterized time evolution afterwards. So it's sort of, schematically a bit simpler of a problem than imagining what you have to do for JLP. So I told you that what they considered is the Kurkcuoglu Hamiltonian. And in the same way that quantum chemistry people have said, well, reformulating my problem in a different basis or reformulating my problem with different, assumptions can get me numerically better answers with the quantum computer in the same way we do classically. The story in lattice QCD is that the Kurkcuoglu Hamiltonian is not the only one we have. In fact, what we really have in the continuum is one Hamiltonian. And for pure gauge, it's really, the electric field squared plus the magnetic field squared. And everything you do to put it onto a lattice is about making choices as to how to approximate that thing. So what Kurkcuoglu does is it takes the lowest order possible thing you can do of finite differencing, and you get a kinetic term and a potential term. And this thing has order a squared errors. So if you're thinking about the lattice resolution, any error you have from the true number you want goes like a squared. But that's a terrible idea. So as we learned from doing classical field theory on classical computers, if you add additional terms, which will add a little bit of extra gate cost, you can knock that a squared scaling down to something like 8⁴, 8⁶, however hard you want to try. And just by choosing a better Hamiltonian, which is slightly more costly in terms of circuit depth, you can reduce the qubits because the error that you're now worried about has gone down by 2 orders of magnitude, or 2 powers. And sort of for the naive scales and for the naive lattice spacings that we sort of think are going to be the reasonable ones required, this is going to give you something like, 2 to the dimensionality of the problem in terms of fewer qubits you're required, just by being more intelligent about what problem you're going to try and solve. So again, to take a high level point of view, what are these like low level primitives that I need for a lattice QCD calculation? So, I need to be able to simulate potential energies and kinetic energy terms. And because these unitaries are going to be very, very large and very, very dense like everyone else, we would like to break this down into as many fine-grained steps that can be independently optimized. And so the picture you should have is, if I'm going to use the Kurkcuoglu Hamiltonian, for example, these are the only 2 sort of register level operations I need to be able to perform. Is the one on the left is the potential energy or the kinetic energy, the one on the right is the kinetic energy. And both of them, and in fact, any sort of gauge theory calculation you want to do, can be decomposed when you consider it at the register level of gauge links into the ability to invert one gauge element for another, the ability to do multiplication in this group that's more complicated and not abelian most of the time. You need to be able to take the trace of whichever element you have, and you need to be able to do the non-abelian Fourier transform for whatever group you care about. So you can imagine that you optimize your architecture in order to design things for these primitive level things, and then a second group of people who are much better at doing real hardware optimization can be thinking of things in terms of these types of primitives that are the things that will always be required to do a quantum calculation for lattice field theory. So as I sort of said, instead of this truncation that takes 24 qubits to do SU3, I'm suggesting that there's one that allows you to do 11. And the idea is that you're going to approximate these continuous groups by a discrete subgroup of them that has the right sort of crystallographic properties. And so at the very, very top, you see S1080, which is sort of the best case scenario we have for doing QCD, which is SU3. And you can imagine that, as we have computers developing better and better, we start at the bottom doing, Z2, as many, many people do both in condensed matter and high energy. And we move our way to the top where we start doing QCD. And so the one thing I can tell you about this digitization scheme is that I can immediately tell you how many qubits it's going to cost. So, what might these registers actually end up looking like? So, the best sort of naive thing you would imagine is that for every link and for every boson and for every fermion, I would just have one qudit that is capable of holding the entire degrees of freedom of that particular state. That would be great. It would make it really easy because then the lattice of QCD is the same as the lattice architecture of the quantum computer. So if you want to do something like, SU3 though, I just told you it takes something like 11 qubits. So that's clearly not one where this works. The more normal thing that most people think about is that you're going to have something like multiple qudits are going to have to represent a single degree of freedom. And what I've done here is sort of tessellated for you the Rigetti Aspen M1 architecture, where what I want to do is simulate a 2-dimensional lattice of a theory where the bosonic degrees of freedom require 3 qubits. So if you put it in this architecture, what you see is not only does it become complicated, but you can do it, but you also see that the connectivity between different links is different depending on where in the architecture you land. So in fact, you have to design different multiplication gates, different inversion gates, different primitives for where you are in the architecture if you land into this particular type of a platform. Then the other sort of ridiculous extreme you can imagine is what SQMS is sort of trying to design, is the idea that you will have such a high Fox state setup in your qudits that in fact you can encode multiple lattice sites and multiple links together in one qudit. And then all of a sudden you're talking about linking qudits in this non-trivial way where parts of the lattice are independently encoded in different qudits. And so each of these 3 particular types of platforms that SQMS is thinking about requires sort of different specialized at the fine-tuning level of how to implement these things. And they come with different gate costs and they come with different error profiles. And the amount with which one of these ends up giving you a total cost at the end is not known at the moment, but they will be very, very different. So we've actually run a few of these primitives for a particular group. So taking the Rigetti Aspen 9 chip, I believe, we actually ran all 4 of these primitives for this so-called D4 gauge group. And what we found is that we can get something like 80% fidelity on each of those primitive gates, which if you remember back to the slide where I showed you what it took to do the kinetic and potential energy, 80% fidelity is clearly not good enough to do a Trotter step with. But importantly, having this CC phase, having this 3-qubit gate is what allowed us to get all the way up to 80% fidelity, which again is not the best we could ever hope for, but it's a lot higher than we would have if we were stuck with a type of platform where all we had was 1 and 2 qubit gates. So I think I'm wildly over time at this point, but sort of in conclusion, this is what Khan and Nam had said. And what I've hopefully tried to convince you today is that while those numbers are the ones that are in the book, they're not to be necessarily trusted as too terrifying because, 1, Instead of doing, hadron scattering, let's just do viscosity. Instead of using Kogut-Susskind, we should use better Hamiltonians. Instead of truncating with that particular digitization scheme, there are other ones that certainly suggest fewer qubits. As many people in this room, in fact, are well aware, the trotterization bounds we often get in terms of what the error is going to be on a real simulation for some particular state that we care about is very, very different than sort of these upper bounds that we get generically. And because this sort of derivation was done with an upper bound assumption, we have reason to think that it's a much, much lower gate cost to really get the fidelity we want. Decomposing into specific unitaries, well, if you have a different platform that gives you access to 3 qubit operations, or all of a sudden you have big qudits, the entire question of what this circuitry is going to look like becomes different and is shrunk, as sort of Eric was talking about yesterday in his talk. And then sort of finally, I know the computer scientists in the room love to use numbers like 10 to the minus 8 as sort of the error you want to consider. But for the particular problem of the viscosity, I would like to point out that as of right now, the theoretical uncertainty on that is more than 100%. So you're insisting on doing much, much better yourselves and sort of wasting both of our times because you can accept much, much worse errors if you have. And with that, I am done. And I will just say, we now have a number to start beating down and try and get something into the realm of reality. Thank you.
I think because of time, we'll just move on, but clearly you guys can find Hank and talk to him. So next is Sohaib Alam.
Hi, everyone. I am just going to try and share my screen here. So can everyone see my slide deck in full screen and hear me as well?
Yes.
Yes. Yep.
Great. Well, so hi, everyone. I'm Sohaib. I'm a researcher at the NASA Ames Center. Unfortunately, I couldn't make it in person, but thanks a lot for having me here virtually. Today, I'll talk about primitive quantum gates for dihedral gauge theories, which is expanding on what Hank just talked about. And it's based off this work that I did with my colleague at NASA, Stuart Hatfield, as well as Hank and Andy Lee from Fermilab. And the general idea, as Hank just touched on, is basically that we would like to approximate a continuous group by some discrete subgroup. So the simplest example is how the cyclic group Zn becomes U1 in the large N limit. But as a simple example of a non-abelian, but still discrete group, we consider the dihedral group, which in the large N limit approximates U1 cross Z2. A generic element of the dihedral group is really specified by 2 fundamental elements. One of them is a rotation. So there's n rotations around the U1 circle. And you could have a reflection or not. So the exponent m of the reflection is just 0 or 1. And as Hank just described, a rather generic way to simulate such gauge theories is if we could have access to these 4 types of fundamental gates, the inverse, multiplication, trace, and Fourier gates, then we could in general perform such a simulation. So this work really just describes how to do this for arbitrary dn in full generality. Now, first of all, the inverse gate is, in my mind, is the simplest gate, and it follows almost straightforwardly from the algebraic properties of the dihedral group. So here, the idea is basically just that if you don't have any reflection, then if you just have a rotation of k steps, then you need n minus k steps to go back to the identity. But if you do have a reflection, then actually the inverse is its own. The inverse of that element is the same element again. And so what that means in quantum circuit language is that controlled on the value of whether or not you have a reflection, you are either doing nothing or you're subtracting k from n. And so that's basically subtraction. And one rather simple way to do this on binary numbers is to perform the 2's complement, which is equivalent to computing the so-called 1's complement and then adding the number 1. The 1's complement is basically just flipping all the bits to their logical opposite. So 1's to 0, 0's to 1's. And then you can add the number 1 by just doing, elementary school addition, essentially, right? Except you do it on binary numbers. And those operations can all be done, fairly efficiently. The multiplication gate, I guess the main thing that I'd like to stress here is that the inverse gate essentially just reduces down to ordinary arithmetic. And the same case happens to be for the multiplication gate as well. Here, it again follows, you can sort of work it out from basic dihedral group properties that that fundamentally, like if we're considering left multiplication, then dependent on whether or not you have a reflection or not in the right element, you're either performing addition on K1 and K2, K1 and K2 both specifying the number of reflections in the two elements, sorry, the rotations in the two elements. And you're either adding them or you're subtracting a K2 minus K1. Remember that R to the n is the identity. And as we just saw, doing subtraction could be done using the 2's complement. And so, this is, again, just a very simple-minded way to perform this very simple arithmetic operation, just using sum and carry bits. And an example circuit for the D8 group, for example, is shown here. So again, the multiplication actually just reduces to binary addition and subtractions, which is particularly nice. Somewhat complicated, slightly more complicated is the trace gate. So here we could think of the unitary that we want to implement as the exponential of some Hamiltonian that is given to us through the trace of the fundamental representations of the gauge group elements. So one way to do this exactly is to basically just implement this diagonal matrix exactly, and you can do this by exponentiating various combinations of z's and i's, right? So if you just allow all sorts of combinations of z's and i's, then you can do this exactly. Of course, the downside is that this scales in n, where n is the subscript in dn, which is of course exponential in the number of qubits. So for small enough size systems, this is nice to do, but not scalable if you want your computation to scale polynomially, for example, in the number of qubits. But you could imagine, and there have been descriptions of algorithms of how to do this. If you have a subroutine that, for example, can compute these classical trigonometric functions on quantum registers, where the tilde here just denotes that you have some binary approximation to these quantities, then you can basically just imagine doing a phase kickback, from these quantities back to the original register, and then you can uncompute whatever scratchpad you use. Just measure out these qubits and force them all to be zeros, and in effect you have computed the trace gate up to the approximation error given by however many qubits you're willing to use to compute these sines and cosines. Finally, the Fourier gate is, to me, the most interesting part. Now, the Fourier transform of a representation over some finite group is described as follows. Basically, f over here just denotes the function values on the individual gauge group elements, and rho, and usually we consider this to be an irreducible representation of this gauge group G. Rho is simply the representations of each of these elements G. Now, this also has a recursive definition. So if we think of G as basically having some kind of a left coset structure, so the GIs are the left cosets of this group G, and H is the subgroup. So in other words, I can express any element in G as GI times some element in H. Then I can write this as basically, the Fourier transform over the entire group can be reduced to a sum of Fourier transforms over the restricted, of the restriction of that representation to that individual subgroup. Now, one thing you have to make sure about this particular irreducible representation is that when it is restricted to that subgroup H, then that irreducible representation of the original group G becomes a direct sum of irreducible representations on the subgroup H, which isn't always easy to find, but in the case of the dihedral group, A lot is known about its irreducible representations and so forth. But for more complicated discrete subgroups, for more complicated theories, this, you can imagine, can become quite non-trivial. So in the case of the dihedral group, the nice thing is that in principle, you could keep on, carrying out this recursion and say, well, okay, so now that I have this subgroup H, I can further, recursively reduce this to a sum of Fourier transformations of its own subgroup and so on and so forth. But in the case of the dihedral group, you can just stop at one step because it's the left traversal that you have is over the cyclic group Cn. And in this case, the left coset representatives are just whether or not you have a reflection or not. So it's a particularly nice structure. And the Fourier transform on Zn in quantum land is something that's very well known. It's the quantum Fourier transform that you read about in Mike and Ike and all introductory quantum textbooks. And so this is basically what this step is performing. Now, the non-trivial step, at least in my book, is actually going from something like this, where now your basis looks like this product of left cosets of G times the Fourier basis of the subgroup Cn into the Fourier basis of the original group G. And that was actually provided to us by this rather old paper by Fourier. And that's basically like, everything after the FZN. So altogether, we put this and we actually do some experiments as well. We run, and in particular, we explore, how these gates might perform on a current day device. At the time, we did experiments in the Rigetti Aspen 9 chip for the D4 group. And we found a process fidelity of roughly 85% and 92% for the trace and Fourier gates, respectively. If you implement the inversion gate for the D4 group, you can see that basically, apart from some single qubit gates, it's the CC phase gate. And the process fidelity of the CC phase gate was approximated to be 87% using cycle benchmarking in this particular paper. So it again is, roughly like, in nice enough regime, I suppose. Finally, the multiplication gate for D4 here, because we have to consider the product of two D4 elements, each of which use 3 qubits. Process tomography on 6 qubits is already kind of prohibitive. So instead, we said, well, you could sort of consider this as, in some sense, as a kind of a classical circuit, in the sense that if you give me bit string inputs over here, then I should get bit string outputs. And so one way to benchmark this gate is to just simply compute the average fraction of correct output bit strings. And without any span correction or any of that, we found this to be roughly 0.89. But if you take the majority vote of 200 successive shots, which, it's not doing confusion matrix inversion, but it is doing some kind of span correction, it boosts up slightly to 0.91. So to conclude, I would say that it's possible to approximate continuous group gauge theories via their discrete subgroups. And for U1 cross E2, this is a thing that I didn't really touch on in this talk, and I'm not sure if Hank did either, but DN, there's some arguments in the paper that show that DN is already a fairly good approximation for N, roughly order 10. And experimentally, we found greater than 80% estimated fidelity for D4 theory on a noisy current day device. More complicated gauge theories and more complicated discrete subgroups. And as I mentioned, for example, for the Fourier gate, you would have to worry about their irreducible representations. Not only that, but also how you restrict them in a particular way to their subgroups, which chains should you consider of subgroups, et cetera. So all that is something to be done in the future. And with that, I thank you for your time, and please reach out to me over either of these two emails.
Sohaib.
Sorry, I heard someone ask a question.
Yeah, so since Sohaib is remote, and won't have a chance to talk with us, maybe we could take a question or two. Does anyone have one?
So Andrew Landau here. So if you looking at discrete gauge theories, the electric charges correspond to unitary irreducible representations, and the fluxes correspond to conjugacy classes. How do you do state preparations for those things? You showed us how to do the gates that are the, doing these various, the representations of the gauge elements themselves, but how would you do state preparations for those kinds of objects in these discrete gauge theories?
That's an interesting question. We definitely did not consider the question of state preparation in this paper. And this is also just for pure gauge theory. So, in essence, if you're you just prepare like a single gauge element, and then you can perform operations on it if you, imagine some kind of like a trauterization step or something. But are you asking how do you actually prepare like a certain gauge configuration?
I'm just saying, when one looks at like discrete gauge theories, one, asks, well, how do you identify what the charges and the fluxes are in the theory? And I know that they correspond to these objects that are like these irreps. You mentioned them, showing up in more complicated groups. Those are the charges, and the fluxes correspond to like conjugacy classes. And it's actually the latter one that I was sort of puzzling the most over, like how would one construct a conjugacy class of a group element as a state? So you presumably want to symmetrize over all the elements in that conjugacy class. You want to construct a superposition over all G in the same conjugacy class. And there'd be some circuit that would do that, that would use the elements that you've shown. There's some way to do Fourier transforms and unitary gates to sort of create such a symmetrized state, So it's a superposition over all things in the conjugacy class. So that state is somehow a representative of the conjugacy class. And I was just wondering if you had thought about that, because that would, I imagine, be an initial starting point for, I don't know, some variation of algorithm you might run or something like that in a discrete gauge theory.
That's an interesting point. I'd have to chew more on that before I could say something. Maybe we could pick up the discussion over email or something later. But yeah, I think in general, considering, like some of these primitives as kind of starting points for variational approaches or other approaches would certainly be an interesting direction to push this towards. One of the things that certainly did capture my imagination here was just how tricky it can be to even implement the Fourier transform for even like simple enough theories like the dihedral group. And as I mentioned, the irreducible representations for this are like very well known and everything, but you still have to think a little bit about like how you can, you need to structure it, the representations and the chain of subgroups in such a way that the required properties hold. I think in the pure math side, they're called like the Gelfand-Zeppelin basis, if I'm not wrong. But those are, if what you suggest it holds true, then for the more complicated cases, like for SU3, where the relevant subgroup is S1080 and so forth, I think kind of like on the purely mathematical side, those are the questions that would probably be, I guess, the most challenging to work out. Like, what are the representations? What are the specific subgroups? In the case of the dihedral group, like you just have a nice chain. But for more complicated groups, you could have a lot of chains that you might want to consider. And once you have the chains, then you also need to consider, well, which irrep, and it's not just sufficient to consider equivalent irreps. Like you really have to make sure that you find one representative of a whole class of equivalent irreps, such that when you go down the chain of subgroups, these really do form direct sums of irreps of those particular subgroups. So anyway, that doesn't really answer your question, but hopefully, it gives you a sense of what I think are probably going to be the most challenging parts if you wanted to push that.
Cool. Thanks very much.
Yeah, thank you for listening.
So next, Doga Kurkcuoglu.
Kurkcuoglu.
What he said.
Hello, everyone. My name is Kurkcuoglu. I work at Formula SQMS. So since like this is the last talk before lunch. I want to be respectful to everyone's time. So let me take it really slow. So today I'm going to talk about a very simple simulation for scalar field theory that we are trying to develop at SQMS. So this work was done mainly by Alexander Macklin at Fermilab, and then we did collaborate with Sohaib, Josh, Andy, Gabe from, and Stephen Providence from Cutting State University. So the motivation is, well, once we have the SRFK cavities running at Fermilab, besides the particle detection, we want to do some quantum simulations. So, and then this is like a transmon coupled to a cavity, where cavity like has very long coherence time, where electrical field just bounces around with a very high Q factor. So that you might have very, very long coherence time such that we have achieved 2 seconds of coherence time in Fermilab. So we can use these electrical field modes to simulate a field. And then the simplest thing we can do is just using a scalar field theory. So just start from the simple Lagrangian. Probably you don't have much explanation. I'm going to skip very quick. So we are going to discretize this Hamiltonian, and then these are just dimensionless parameters, and then each of the phi 0, phi 1 are going to represent my discretized field, and I'm going to expand these fields into harmonic oscillator eigenbases, and then I'm going to make another discretization in the cavity basis Fock states. So it's going to look like this. So like before moving on to that, like our group also studied a similar field theory in qubit systems, where we used like many T gates to simulate one field actually. Now, the main thing is, the punchline from this talk is you can use qudits to simulate each field, and then if these cavities are connected, you can simulate multiple fields that they are entangled, and then you can use a new technology called like snap gates, selective number arbitrary phase gates, to reduce the number of T gates. So that's the punchline of this talk. Okay. So this is how the cavities are going to look like. This is only one cavity. Imagine that like we are going to just connect multiple cavities, for example, 9 cavities, and then we are going to connect one transmon, and then transmon and the electrical field can be manipulated arbitrarily by using optimal signal or other things, other methods. So let's say we are trottarizing the Hamiltonian, and then in order to trottorize this scalar field, we need to have these gates, where this is the theta is an arbitrary angle, and then pi is the trotter step in momentum basis that requires making a QFT for a single qubit. Okay, so we need to define what the QFT is going to look like in this SRF cavities. So this is the schematic. Imagine that these are all, this is one cavity, this is another cavity, and then these are the Fock states. I'm going to make a cutoff. So each of the field is going to be discretized into second discretized into harmonic oscillator functions, and then these states are going to represent my field. Okay. When I discretize, the penalty is going to be like okay. I'm going to show you in a minute. So if I discretize, for instance, if I have like 24 Fock states, a simple Gaussian function is going to look like this. Basically, I'm going to make a trotter step in amplitudes of the Fock states. Okay. Now, so basically, the simulation depends on these coefficients in the Fock states at each cavity. Now, so I'm going to discretize with x. X is the discretization on the field for function. Sorry, and then J mu is the discretization for the field itself. Okay, and then the penalty I'm going to have is the this auxiliary function due to Nyquist-Shannon theorem, because I'm discretizing. So okay, so the main thing is instead of like you applying many phase gates for qubits, I can use one snap gate on each of the Fock states in one qubit. Okay, so the way that this phase gates works is first. So this, if I imagine only one qubit coupled to one cavity, basically the Hamiltonian I'm going to have for the system is going to be James-Cummings type of Hamiltonian. And then I can excite the transmon with a photon number dependent frequency. And then once the qubit becomes the excited state, I can make a Z rotation in the Bloch sphere of the qubit. And then that's going to be the number dependent phase for the Fock state. And then I can apply the same number, the number dependent frequency to the qubit, and then take the qubit back to the ground state. So during this process, for Fock state, the entangled single cavity and the transmon wave function is going to gain a phase. And then this phase is going to be, since I'm exciting the transmon with the number dependent frequency, it's going to be number dependent. Okay. So that's the main idea. So yeah, here, first I'm going to take the qubit, excite into the ground state with this number dependent frequency. Okay. And then make a Z rotation, and then take that back to the ground state. And then this solid angle in the Bloch sphere is going to be the phase I'm looking for. Okay. Now, okay, I can make this, I can use the snap gates on each qubit to make a trotter step for the field. But the snap gate is diagonal. If I want to make a momentum step, I have to transfer this state into momentum basis, which requires, like, it's actually a dense matrix. So if I want to engineer a quantum Fourier transform, I need to use another gates. Now there's a theorem says that I can, if I take a U n by n unitary gate, I can decompose this n by n unitary gate with only snap and displacement with arbitrary choice of parameters, appropriate choice of parameters. Okay. Now, displacement gate is basically like what you have learned already in the introduction to quantum mechanics class. It's just to create a coherent state. But for our cavity system, it's going to be a little different, which I'm going to talk in a minute. So imagine that, like, I create a block from displacement, snap, and displacement gates, and then I'm going to use K blocks to decompose this gate. Okay. Now the target gate is going to be our Fourier gate. Okay. Now, one thing is the difference between the textbook displacement gate and the actual displacement gate is like displacement gate in the textbook is infinite by infinite and requires like A dagger A operators. But the thing is like in actual cavity, the displacement gate is truncated, which is going to couple the logical states and the unwanted states in the Fock state. Okay. So in order to monitor that unwanted state, we just introduce a bumper state to, so the target unitary is going to be here, which is going to be the Fourier gate. And then this is going to be just to make sure that there's no leakage besides the logical gates, okay? Because A dagger is going to be basically couple the logical states to the bumper states, okay? Now, how to find the parameters? So we are using this cost function, and then we are using this ansatz. And here you go. So for instance, like this is the, I'm showing you an example for 60 logical state for bumper states. And then like it requires actually like, and then the number of blocks are going to also equal to the 64. And then although like this requires like a lot of parameters to optimize, so it took just 40 minutes, and then we can easily go up to 250 or more states. Okay, and yeah, and then one thing is in order to make this, so this is coming from the momentum state, sorry, kinetic energy trotter step, phi j phi k trotter step. So in order to do that, I need to use a conditional snap gate, which requires like I have two cavities. I'm going to change phase of the one cavity based on the conditional on the photon number on the second cavity. Okay, So basically that requires like straightforward application of, I need to excite the transpond with photon number, second photon number frequency based on the cavity number 2. So, and then this is the simulation. First, we prepare the state, and then apply the 5/4 throttle step with snap gates, mass gate, mass term, Fourier gates, which we found the appropriate parameters with the variation algorithm, and then another kinetic energy step, and then Fourier gate. So, and then also, coupling term between kinetic energy term. So the number of gates, snap gates and Fourier gates are like much lower compared to the qubit counterparts. Like for instance, like for these simulations that I'm going to show you, like these are, I did that with the like for 500 snap gates only. Okay, so this is, I'm showing you 3 qudits, which means 3 fields, and then 500 snap gates, and then 16 gates, 16 Fox states, where 12 logical states and 4 bumper states. So, and then as I made my throttle step, I'm changing the G, which is the 5/4 coupling constant, and F, which is the phi J, phi K coupling constant adiabatically. Okay, and yeah, I just want to show you the conclusions. So by using the SRF cavity, using the circuit QAD, and using snap gates, it just gives us an alternative way to quantum simulate the field theories. So this was a preliminary, basically, example, basically like a toy example to simulate the field theory. And then, yeah, thank you very much.
Why don't we ask questions over lunch? And lunch will be, we got about an hour and a half for lunch. We'll be back at 2 o'clock. Thanks.
So anyone wants a tour of the building at 1:30. So show you around. There are lots of services. So anyone
I mean, what did you do? So I think you showed before. Yeah. So here, right? If you get this 10⁻², yeah. So what do you know? What can you do to increase it?
Just wait for more iterations.
More iterations in what? Optimization or just a couple like
Like basically like I define the cross function.
Yeah.
And like in order to like I just for I need to decrease that number.
Okay. I guess that's my question.
But it's exponentially.
Okay, I see. Just you know, this problem is basically the same as you know the problem of what one could call the optimal control problem, right? You just want to find the parameters of each of the gates. And so when you have a finite dimensional system, when you know the depth is long enough, there are some results that guarantee that you have a very good solution, and that the optimization also, you know, works well in the sense that once you cross some threshold number of iterations, you won't really gain much. You get, yeah. And I know that for non-complex groups, so that's asking about something. Okay. Maybe I should stop recording. Stop recording.